Good morning to all, a warm welcome. So in today's video, we will discuss about gas chromatography, its principles and application. We will also see a live demo at the end of this presentation. So introduction, coming to introduction, we know that gas chromatography is a technique of separating volatile gaseous substances by using a gas or a mobile phase. So gas chromatography is an analytical methodology which is invented by the Nobel laureate Martin in the year 1952. So since its development, there has been a numerous improvements in the GC for various industrial application for its quantification and qualification. So coming to the application of GC, as I was telling, it is used in residual pharmaceutical analysis. If you go for a pharma company, at each stage, say raw material will be analyzed and tested by the GC. The intermediate products at each stage will be tested by the GC, and also final product has to be tested because it has to meet the specification of the pharmacopoeia which they have been following, whether it is Indian pharmacopoeia or American pharmacopoeia. There the limits of the impurities will be mentioned. So we have to analyze and approve at each stage for the minimum limits of its the products which is present in the sample. Similarly, in the pesticides analysis, so recently we would have got to know about this Maggi. We have more amount of pesticides in the Maggi. It means it's not pesticides, it's an impurity which is not been which doesn't, or which they have not ensured to test and remove during the release of a certain batch. So this batch has a certain has certain more amount of the impurities which is present in the food. So only there was some issues. They have been asked to take back the samples and also analyze it at a different at a quantify at a different instrument, or things were like that. It is also used in trace level analysis for environmental as well as pharmaceutical and fine chemical industries. So GC finds numerous applications whenever we enter any pharmaceutical, petroleum refining industries, or any environmental or food safety industries. So next we will differentiate between the term chromatography, chromatogram and chromatograph. So what is chromatography? So chromatography is a method of separation. Chromatogram is an instrument which is used to analyze the to detect the chromatograph, and chromatogram is a graph. So chromatogram is a graph and chromatograph is an instrument, and chromatography is a technique. So what are the other chromatography technique which we know? We know thin layer chromatography, liquid chromatography, and also ion selective chromatography, many things. Right. Yeah, what is the principle? Next, going to the principle of gas chromatography. So it involves the relative distribution, which they call it as partition, between the sample components between a stationary phase and a mobile phase. So stationary phase can be a solid phase or a liquid phase, and mobile phase is a phase which is always running through the GC. So preferably mobile phase is a gas phase. So when we inject a solute, the solute gets distributed between the solid or liquid stationary phase. It gets eluted based on the molecular weight. Say for example, if we take two compounds, one lighter compound and one heavier compound, this lighter compound will not be retained, or will be retained and it will be eluted quickly, whereas heavier compound, say methanol, any organic compound, it will be retained for a little longer time and it will get eluted and comes at the last. So based on the relative distribution of the sample components between the liquid phase and the gas phase, we get the peaks. Okay. And the major components of the analysis are stationary phase, which is it can be a liquid phase or a solid phase, and mobile phase, which is a gas phase. So coming to the components of GC, we have a carrier gas which flows through the column. We have an injector in which the samples are injected. We have a column through which the separation happens, and we also have a detector through which we can quantify what are the products which has been analyzed. So here you can see this is a carrier gas, it is a cylinder, and then it should be a high purity cylinder, because to get the minimum quantity of reduction in the ppm or ppb level, we should have these cylinders. Okay, and we have an ejector port through which the samples or solute is being injected we have a detector through which the elution happens, which is being electrically transferred into signals in the data processors. So usually GC will have only one carrier gas. If you have 2-3 columns inside the oven, you have separate 2-3 carrier gas. But if you choose a flame ionization detector, you have 2 more cylinders for creating the flame, like hydrogen and oxygen cylinders get added. Coming to the instrumentation of GC, preferably about the carrier gas. So if you talk about carrier gas, we have said that what is the role of the carrier gas? The role of the carrier gas is to move the solute along the column. So it is also known as mobile phase. So what could be the desired characteristic of the carrier gas? It should be inert. It means it should not react with the solute which is being sent to the column. It should be readily available and it should have a very good flow rate. Like they say linear velocity, that should be available. So different carrier gas which is being used is argon, hydrogen, nitrogen, helium. They also use certain other carrier gas for any other specific purposes. So with respect to cost, if you compare, helium is the costliest gas, followed by argon, and hydrogen and nitrogen will be the same amount. So we are talking about this gas because we need this gas at a high purity of 99.99%. So when only if we have high purity gases, then we have a good deduction. Coming to this injector port. So you can see the diagram of an injector port here. So the carrier gas is already in flow through the column and we have a heated metal block in the injector port. Okay, the samples which is being injected will be heated and it will be converted into vapor. Okay, this is a syringe. It's a micro syringe. It can be a gas tight syringe or a liquid syringe, and there is a septa, rubber septa, which ensures that the gases are sealed inside and it is not leaking anywhere. But when we continuously use this, the rubber septum is a consumable and we have to change this septum frequently to ensure or to prevent the leakage. If this is leaking, we will not get any peaks in the GC. So we should take enough care to change this septum frequently. So as we see, the liquid sample is injected by means of a calibrated microsyringe. The sample is injected through the rubber septum at the head of the column, and the sample, what volume of the sample you can inject? If it is a liquid, you have 0.1 to 10 microliter is enough. If it is a gas, you need to inject a little higher volume of about 1 to 10 ml is injected into the column. So the temperature, why do we have a temperature or a heater here? Because all the liquid samples can be converted into vapors without undergoing any other further decomposition. So you can see the syringes. This is a liquid syringe, this is a gas tight syringe, and this is a septa, the rubber septa. So it's you have to use or frequently change the rubber septa. But when we have the continuous injector, then in that case the scenario is little different. So coming to the instrumentation of the GC as a columns. So let us just discuss the column. There are two type of column. One is stainless steel column or a glass column. Okay, so it will have 2 to 3 meter long. If it is a stainless steel column, it will be 2 to 3 meter long or maximum up to 5 meters and diameter could be 2 to 4 mm, diameter of 4 mm. So here the solids has been packed tightly for the elution. So here you have packing such as silica gel, alumina, charcoal, molecular sieve as an adsorbent in the gas solid chromatography. So some of the columns are molecular sieve column, Haysub column, and also zeolite based column can be used for the GCs. Next, coming to the capillary columns. So capillary columns will be of this kind. You can see in the figure, it will be so lengthy and it will have very thin diameter. So the internal diameter is 1 mm. It will be more fragile. It is all glass columns. It has been coated. A thin layer of liquid has been coated inside the columns. So it's called, it can be either like, it's a wall coated open tubular column or support coated open tubular column. But it will be very thin of about 1 mm or 0.25 to 0.3 mm of diameters. It will be lengthy. Length can be 5 meters, 15 meters, or it can be up to 100 meters long. So the column, it doesn't contain packing as like stainless steel column. It has only the liquid which is coated or which is during the manufacturing only, on the very thin layer of the liquid has been coated on the glass. So example, plot column, plot Q columns, DB5 columns. So this for this one, based on the polarity, based on the change in polarity, the column supplier will give numerous column for the specific applications. So coming to the detectors, so I have discussed about two detectors here. One is thermal conductivity detector, the other one is flame ionization detector. We also have electron capture detector. So the viewers can take the details of the electron capture detector from anywhere else. What are the qualities of a good detectors? A good detector, as it being used for detection, it should be good sensitive, should be stable, it should be selective, and it should give a linear response as an output. Okay, so now let us discuss about thermal conductivity detector. This thermal conductivity detector works on the principle of Wheatstone bridge. It have two filaments. In the two filaments, one the standard gas flows through the filament, and the gas along with the carrier gas flows through the other filament. So when it flows to the filament, when there is two carrier gas flowing, there will be no change in the thermal conductivity. But when we have a carrier gas along with the sample which flows, there will be change in the thermal conductivity, and this thermal conductivity can be recorded as the difference in the thermal conductivity is recorded as the peak, right? You can see the pure gas flows through one arm of the Wheatstone bridge, it's called reference, and the eluent means the carrier gas and the sample flows to the other arm. So it is a non-destructive detector. What it means? Non-destructive detector means the whatever the gas composition is being eluted it is same. It is not diluted. It is not, nothing has been done to the carrier gas and the samples. It can be passed to the next detector for analysis. So it is non-destructive detector. Coming to the flame ionization detector. So here I could say it is a destructive type of detector. Why? Because whenever the column with the sample flows, it is being burnt in the flame, and it has been converted into ions. So here you need two extra cylinders to create the flame. One is air or oxygen cylinder with a high purity along with hydrogen cylinder. So we used to ignite here to create a flame before the GC injection has been made. Okay, so here you can see we have a ring electrode and we generate a flame, and whatever sample it is coming, any organic, any sample is being burnt, and it is converted as the ions. These ions is being sent to the amplifier, and then from which the signal has been detected as a peak. So it is more sensitive. It is used for carbon containing compounds. So you can see it is 1000 times more sensitive than TCD detector. But it has some limitations. It cannot detect permanent gas. It can detect only mostly organic based gases. So it should, when it burns, it should produce some ions. So it can detect up to ppb level based on the purity of your carrier gas, and also based on the column. You can go up to the detection of parts per billion levels. So we have understood all the individual components of the GC, right? So it has a gas cylinder with a high purity which acts as a carrier gas. It flows through the column and it helps in elution. So there is a flow controller. Okay, this flow controller helps in controlling the gas flow rate, and also has an indicator. If the flow rate is low, the column will automatically will switch off, because if you are running a GC without a flow, so it might harm the detector, and it also harm the column. So because in the oven also it will be a higher temperature will be maintained. So when you are heated it and there is no gas flow rate, it might harm the column. So we should ensure that always the gas is being switched on first before switching off the GC. So we have an injector port. As I discussed, you can have one or two injector port based on the columns which you have. You have a detector, so that you have one or two more detectors based on the different type of analysis which we have to do. The detector can be parallelly connected or it can be seriously connected based on the choice of your elution. And from the detector, all the electronic signals are sent to the data processor and you get the peak. Yeah, this is a gas chromatography. So I will show the demo of a gas chromatography. So you have a column, this is an oven. So inside this oven you have a column, so you have a display, and you also have a timer. This timer helps me in switching the analysis from one column to the other column. Okay. So these are the flow controllers. So we can go and see a live demonstration of the GC. where I will also show with an injection like how the peaks are eluted from this gas chromatography. So here we have a gas chromatography which is purchased under DST's startup research grant, and this mainly has your mobile phase as a gas with a stationary phase as a solid or a the gas chromatography has three different gases. Here we have a carrier gas, and hydrogen and air is used as the gas for detectors, for combustible purposes, preferably for the detectors. So this panels indicates the pressure which is maintained inside the column. Carrier gas is used as an organ, is used as a carrier gas. We have two different columns, preferably capillary column and packed column. So for capillary column, also organ is used as a carrier gas, and packed column is connected in series and it is connected to the detectors. Apart from that, we have an injector. We have two injectors separately going for the two different columns, and also we have two detectors, FID connected in parallel with TCD detectors. So we have a timer setup here for switching the column from one packed column to the another packed column. We also have injections facilities for injecting in liquid mode and also in gas mode. So coming to the applications of the computer is constantly connected to the GC for data acquisition. Here we have two different softwares. First is called EZM Viewer, which helps in maintaining the temperature for the oven, for the injector and also for the detectors. We also have a peak ABC where we can see the peaks by starting the acquisition button. So we have two different channels. So one for seeing channel A is for TCD and channel B is for FID. So now as we see here, there are two different columns. One is packed column and one is capillary column. So in packed columns, packing such as molecular sieve, HACEP, alumina, silica gel, all those can be packed inside the column and it is connected to the detectors. In capillary column, the diameter will be very small of 2 to 4 mm with length of about 5 to 3 meters, and it has been coated, it is a very thin liquid coated on a glass coatings. Now we have taken a gas sample in the gas tank syringe and we will be injecting in the gas injection port with a small demonstration. Here in channel A and channel B, the acquisition has been started where the peak starts appearing. Now, since we have injected a known volume of the standard gas, so we can see the peaks at the proper retention time.
So we have analyzed a standard gas with a composition of permanent gases such as hydrogen, CO2, copper monoxide, and also we have gases such as oxygen, nitrogen, along with CO2, methane, ethylene, ethane in our system. So we have taken a standard gas canister and we have injected into the GC. So from the TCD analysis, we can see that the hydrogen comes out at less than 2 minutes, followed by the shift. So this shift is locking one of the column and letting only one columns to connected to the detector. So since it is a permanent gas analysis, I don't see much peaks here, followed by which when the column is shift is open, I get oxygen and nitrogen as a peak. Similarly, when I go for FID analysis, I can see in this region, I can see all my hydrocarbons coming out. So here you can see the absence of nitrogen followed by the shift peak. So when the one column is connected, I can elute CO2, I can elute ethylene, ethane, acetylene. Again there is a shift, so that again the columns are in series, followed by which I can detect methane and carbon monoxide. Okay, so this is the peaks which I get from standard gas analysis.